For this week's assignment, we wanted to add the ability to control trim on our aircraft and see how different impulses would impact the motion of our airplane in these different trim conditions. So obviously our first task here was to be able to compute the trim conditions for our airplane. First of all, we're just setting gamma here to 0 degrees and r as in the radius of motion to infinity so that our target is just simply a straight line. Obviously you can change those if you want different target motions. Then all we need to do in this document here is to set our initial conditions for x naught and its derivative here. We can then see how this runs in our simulation. As expected, the plane simply is able to control its trim and head off in a straight direction. You see initially some corrections need to be made, and there's some numerical error that eventually adds up over time, but these are all very small values. Our next task was to be able to compute the transfer function model that'll be used in later assignments. These transfer functions use some imported coefficients and constants, and then I simply use these calculations here, that is from the slides, in order to create the transfer function variables that are finally displayed here. One specific thing that I needed to do was actually create two different derivative functions, right here and here, for our TP partial derivatives with respect to delta t as well as our VA. Our final script here is our steady state model, which imports these different matrices using the previous A and B matrices. I had to look up the coordinates in the other matrix for all the values we needed, but once we did that here, we're able to simply compute the eigenvalues for lateral and longitudinal, which is shown here and down here as well. And finally, we had to calculate the damping just simply using these functions here, which is able to give us the natural frequencies. Here we have our negative poles, which respond to a roll mode, as well as these conjugate pairs here, which will show Dutch roll characteristics in some of our motion. The longitudinal poles have two conjugate pairs here. In order to tell which one's which, we can look at our frequency here. The larger one corresponds to a shorter period, so we'll see that one damp out a lot quicker than the second one, which will correspond to our phugoid mode. We can then see this in action here by hooking up different types of impulses to our simulation. So the first impulse here runs after 10 seconds, and what it's doing is it's exciting the longitudinal modes by using just a simple impulse on the elevator angle here. So when we hit 10 seconds here, we see the impulse happen, but everything is able to correct just right after that. We see some short settling times here for our short mode, but we also have some longer settling times indicated like here, 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 and those ones correspond to our phugoid mode. We can see that here in our poles for longitudinal modes. The next thing we can do is hook up a doublet to our aileron trim, and this will create different modes from before because we're now in our lateral motion here. So when the doublet hits at 10 seconds, we see it just kind of spin out of control for a second and then start heading off. That spin that you see at the beginning, these angles here, that corresponds to our Dutch roll in these lower frequency conjugate pairs. And then these longer settling times, or where it just drifts off to the end, that will correspond to spiral divergence, which is a lot slower. You see here how this will eventually spiral out of control as it slowly loses altitude and keeps spinning around and just flies around the plane here. Our final mode here uses another doublet on the rudder, and these two things are kind of corresponding together, and we'll see similar but not exactly the same results to the motion of the aircraft. When the doublet hits, we see similar Dutch roll movement here corresponding to those eigenvalues, but eventually the yaw will also dissipate a lot slower, which corresponds to our phugoid mode that we saw previously.